Hi everyone, welcome. Today we're going to learn about molecular polarity. Before we do though, I want to watch this little clip. We're going to see a guy, and his name is Danny, and watch him do some pretty cool tricks here. Okay, so you might be wondering, how does that relate at all to molecular polarity? First, I have some questions for you. It could be he's just a really good film editing guru, or maybe it's magic, right? We're actually going to learn today how this does relate to molecular polarity, and you're going to learn how to do this yourself. So let's talk about what we really want to learn about today. So after today's video, you should be able to determine whether or not a molecule is polar using the molecular formula and the Lewis structure, and then also to understand why polarity is important. Prior to watching this video, you really should understand how to draw Lewis structures using the molecular formula and have a basic understanding of electronegativity, how it's determined using trends on the periodic table, as well as determining if a bond is polar based on the difference in electronegativity between two atoms. So let's talk about how we can tell if a molecule is polar. A polar molecule is one that will have a negative and a positive end. We call this a net charge separation, or a dipole. Here's an example. Hydrogen fluoride has a positive end and a negative end. We see here positive end, shown here illustrated in blue, and the negative end in red. This is due to the fact that the electrons are not shared equally between the elements. Fluorine pulls the electrons much more strongly than hydrogen does, and that gives it a negative charge in this region, leaving a positive charge here. Now, we could also take a look at hexane. Hexane is an organic molecule that's nonpolar. Notice that there are no ends. It's all the same color, and that's due to the fact that there's a small, very, very small difference in electronegativity between the elements involved. It's not strong enough to create polar bonds. So this raises the question, since we can't see molecules with the different colors around them to indicate if they're polar or not, how do we determine if a molecule is polar? There is an easy four-step process to doing so. The first thing that you want to do is draw the Lewis structure. Second is you want to determine what the molecular geometry is, whether it's linear, tetrahedral, etc. Third is to identify if there are bond dipoles. This is done based on the differences in electronegativity between the elements involved. Fourth is to determine if there's a net dipole moment. And you do this by adding together all of the bonds and seeing if they cancel each other out. So let's take an example. Carbon dioxide. Draw its Lewis structure. Determine the molecular geometry. They're all in a line. There are only two domains of electron density around the carbon. That gives us a linear molecule. Question of whether or not there are bond dipoles. So the difference in electronegativity is that oxygen has a greater electronegativity than carbon, and it's large enough that there are bond dipoles. We would indicate this with some arrows. The positive indicating that there's a positive charge in this region, and the arrow points to where there's the negative charge. Finally, is there a net dipole? We can do this by overlaying the two sets of arrows. And notice that if they were to overlay each other perfectly, that they would cancel each other out. Because they do that, they cancel out, the molecule is not polar. Now, when we look at the color map here, we can see the blue for the positive part of the molecule and the red indicating the high electron density or the negatively charged portion of the molecule. But notice that there are not two different types of ends. There is positive and negative, but one end is negative, the other end is negative. Because of this, the molecule is not polar. Let's take a look at another example. Water. So its Lewis structure is the following. Water's molecular geometry is bent. Let's take a look at the bond dipoles. So hydrogen is much less electronegative than oxygen. Therefore, there are bond dipoles, and they point towards the oxygen. Is there a net dipole moment? Well, because it's bent, because it's not linear, when we add them together, they don't cancel out. Instead, they add together and give us a net dipole moment. So, bond dipoles don't cancel, the molecule's polar. It's as simple as that. When we take a look at it, the color diagram, we see that there's the negative region up here by the oxygen and the positive region here. Now, this arrow popped up here. This is another way to show that there's net dipole moment, that the molecule is polar. It's the sum of these other two arrows. All right, now let's take a look back at what was going on here with the comb. So what we didn't see is that the comb had actually been slightly modified. And what was done was that Danny had charged the comb, if you will. He probably rubbed it up against some kind of fur or carpet or rug, and that imparted a static charge on it. Because that made the comb have a negative and a positive charge on it, giving it different ends, the water molecules aligned up so that way they as well were aligned with the negative and the positive end of the comb. And this pulled the water molecules towards the comb because it was attracted to it. There you go. Now you know how he did it. Now you can do it as well and understand it. Okay, so why should we care about molecular polarity? So other than the fact that you can now be an awesome water bender, just like in the movies, molecular polarity actually plays an important role in terms of the world around us. Soap is a great example. When we get dirty, dirt for the most part is made up of non-polar substances. But if you were to try and wash it off, they would not mix well together. And so we have to use molecular polarity and the differences in that to take care of the problem. In soap, there exists within the same type of molecules a non-polar end and a polar end. They'll mix together, and that will allow the soap to mix both with the oils and the fats that are on your hand and pull them up and then be washed away by the water. We also see that it's important when it comes to DNA. DNA is made up of molecules that have hydrogen bonding in them, which is a special type of polarity, or is based on polarity. And because of this, this allows the DNA to make the double helix and to easily unwind but still be stable under most circumstances. Finally, it also applies to food. Mayonnaise is made of polar and non-polar molecules mixed together. And we use an emulsifier. It's a compound that has both a polar and a non-polar end in order to combine the polar molecules with the non-polar molecules, resulting in the mayonnaise that we know and love. Without utilizing molecular polarity, we'd get mayonnaise that looked like that. Not too tasty, I don't think. So, I hope this helped you to understand about molecular polarity, both how to determine it in a molecule, as well as why you should care about it. If you have any questions, feel free to post a comment below, and I'll see you later. Have a great day.